today's class, we are going to learn the different type of curves, their applications, and how to draw them. So, the profile of number of objects consists of various type of curves and various type of curves which are commonly used in the engineering practice are shown below. The first one is the conic section. These you guys are very well aware of. These like ellipse, parabola, hyperbola. These are called the conic sections. Second one is the cycloidal curves. Third one is the involute, then evolute. Next is the spirals, and the sixth one is the helix. So the first four are in the drawing course. So first one is the conic sections. So what are they? A conic section is a curve formed by intersection of a plane and a double cone. So what is the double cone? It is your cone, and now it is your double cone. This is called the generator. This is your vertex, and the circular part at the bottom, it is called as the base, and the line at the middle, which is drawn as a dash dot. In the first video lecture, I have already told you this line is called as a center line. So a cone is a surface generated by rotating a straight line such that it always keeps contact with a closed curve called base and contains a fixed point, that is vertex or apex, which does not lie in the plane of the curve. Or in the other words, you can say that if you take a triangle, you can say that if you take a right angle triangle and you rotate it, taking the height as the axis, means suppose it is your right angle triangle and you are rotating this triangle about this as the axis, then you will get a cone. Okay, and this hypotenuse, which is generating the cone, is called the generator. When the base curve is a circle and the line joining the center of the circle to the vertex called axis is perpendicular to the base, then the cone is called right circular cone. Okay, so if the axis is perpendicular to the base, then it is called as a right circular cone. Thus, the surface of a right circular cone is produced by rotation of two straight lines which cross at an acute angle equal to the half of the apex angle of the cone. So basically, apex cone is, this angle is called as the apex angle. One line shown vertical is the axis of the cone, the other line is the generator. Each of the double cone is called as a nap. When a right circular cone is cut by section planes inclined to its axis at different angles, 5 different type of curves of intersection are obtained. These boundary curves are called as a conic sections. So whenever a plane is cutting the cone, double cone, then we are getting the 5 type of curves. Those are circle, ellipse, parabola, hyperbola, and isosceles circles. Sorry, isosceles triangles. So first, starting with the ellipse, the plane that intersects the cone is neither parallel or perpendicular to the axis of symmetry of the cone and cuts through both sides of the single cone, then we will get the ellipse. Or you can say the inclination of a cutting plane B, that is angle B. Okay, that is the inclination of a cutting plane. It is showing the B is showing the angle is greater than the semi-cone angle alpha, means it is the half of the apex cone. Okay, we get an ellipse as a section. So in the picture you can see this plane is uh, making an angle of B from the vertical plane. So basically suppose it is your vertical line, okay, or you can say this line can be passed through the axis also. So this angle is B, okay. So this inclination of a cutting plane B is greater than the semi-cone angle, means this is your A or alpha, whatever it is. So B is here greater than the A. B is greater than the A. Next is the parabola. The plane that intersects the cone is parallel to an element of the cone. Then we will get the parabola, or in other words, the inclination of a plane B. Inclination of a plane with vertical B is equal to the semicone angle A. Then we will get the parabola. Okay. And the next is the hyperbola. The plane that intersects the cone is parallel to the axis of symmetry of the cone and cuts through same sides of both of the generators. Then we are getting the hyperbola, or in other words, the inclination of a plane with cone axis, that is B, is less than the semicone angle A. Then we are getting the hyperbola. Okay. So here are some other pictures of the parabola, hyperbola, and ellipse and circles. So in this video you will understand uh, uh, how the parabola, hyperbola, and ellipse we are getting. So here the angle B is greater than the A. Then we are getting the ellipse. And if it is parallel to the base, we are getting the circle. Then the hyperbola. So again it is showing the ellipse. And now we are getting the parabola. And this is how we are getting the hyperbola when the angle B is less than the A, cutting both of the cone from one side of the axis. And actually in the last video I think I have missed this one. Okay, so this is how we are getting the parabola when the plane is parallel to the one of the generators. And so the angle will be equal, A equal to B. So the conic may be defined as a locus of a point moving in a plane in such a way that ratio of its distance from a fixed point and the fixed axis is always constant. The fixed point is called the focus and the fixed line is called the directrix. So the ratio of distance of a point from the focus to the distance of a point from the directrix is called eccentricity. Okay, so in the diagram you will understand that easily. So it is your directrix, that is a fixed line. Then it is a fixed point that is called the focus. Okay, then we are getting the a curve and any point on this curve, okay, having the same ratio when we are getting this distance from the focus on the numerator, distance of this point from a fixed line, that is a directrix, in the denominator. Okay, so this is called as a vertex. This is your conic curve. This is your point P, and this also distance R. Okay, each and everything is showing in the figure, and eccentricity is showing by E. It is always less than 1 for the ellipse. It is equal to 1 for the parabola and greater than 1 for the hyperbola. And these things actually you have already have learned in the 11th or 12th. Okay. The line passing through the focus and perpendicular to the directrix is called the axis. The point at which the conic section cut its axis is called the vertex. When we are talking about the ellipse, of course there are two directrix, two vertex, two focus. Okay, and there is a two axis. One is called the major axis and second one is called the minor axis. So, and the vertex on the minor axis is called the co-vertex. Okay. So it is your parabola where we are getting the only one focus and one vertex and one directrix. Then it is a hyperbola where we are getting again the two focus and the two directrix and asymptotes. These are called the asymptotes. So in this picture you can see the when the eccentricity is less than 1, eccentricity is equal to 1, then it is a parabola. When the eccentricity is greater than 1, it is the hyperbola. And when the eccentricity is infinitive, then it is a straight line. So these are the degenerate conics. Actually, when a plane, okay, is passing through the vertex of the cone, then we are getting only a point. Then when the plane is passing through the generator, touching the generator, then we are getting a straight line. When the plane is cutting the cone through the axis, then we are getting a triangle. that is called the isosceles triangles. Here are some real life examples where the conic section have been used. Is the sign of the McDonald. They have been used a parabolic shape. So they have been used the parabolic shape for the alphabet M. Here you are seeing the how the fish is jumping, and when they jump, they create a parabolic curve. In the similar way, if you throw a ball in the air, then it will take a parabolic curve and comes to the ground. Then here you can see these some civil structures, like it is a suspension bridge where the cables are making the parabolic curves, and it is your Eiffel Tower where at the base they are having the parabolic curve at the base. Here you can see the fountains are making up the parabolic curve, and here it is tunnel, those are having the parabolic curves. It is a satellite disk, and you can see how the parabolic shape is. So here is some example of the ellipse. Okay, so it is here you can see the big ball is having the elliptical shape. Here the top of the building is having the elliptical shape, and the egg, this egg is also having the elliptical shape. Then the spoons, you can see spoons are having the obviously the elliptical shape, and it is a building from the China. Okay, and this is having the elliptical shape. You can see the mirror image at the bottom also. As you know, when the planet are revolving around the sun, they create the elliptical shape of hyperbolic curve. It is the chimney. In the in we if you go uh, to the industries, they are having the chimneys, and those chimneys always have the hyperbolic curve. Then it is a guitar, and as you can see, the guitar is having the hyperbolic curve. It is your sand clock, and it is also having the hyperbolic curve. Then it is the best example that means you can see at your home whenever you switch on the lamp, and you can see it is making a hyperbolic curve. Or you can also see by using a torch how. And here are some civil engineering examples, and you can see how the hyperbolic curve is used to create the tower. Okay, so the another curve, cycloidal curve, and this curve was generated by a fixed point on the circumference of the circle, which rolls without slipping along a fixed straight line or a circle. So basically, if you are having a, suppose you are having a circle, and on the circle there is a point on the circumference. And when the circle rotates, so the path of that point is making the cycloidal curve. The rolling circle is called as the generating circle. So the circle which moves is called the generating circle, and the fixed straight line or the circle on which the circle is rotating is called as a directing line or directing circle. Cycloidal curves are used in the tooth profile of the gears of a dial gauge. So basically, uh, it is of these cycloidal curves are very much useful in the mechanical engineering. So here you can see there is a point on the circumference. Okay, so when this circle moves, the path created by this point on the circumference of the circle. So this red line is showing the cycloidal curve. So now trochoid is a curve generated by a point fixed on a circle within or outside its circumference. So in the previous diagram, we have seen the point was on the circumference of the circle. Now the point may be inside or outside and circle is moving. Okay, then we are getting the trochoid. So when the point is within the circle, the curve is called inferior trochoid, and when the outside the circle, the curve is called the superior trochoid. So in the picture you can see the this is the point which is outside the circle, and this is the point which is inside the circle, and this is at the circumference. So when the circle moves, we are getting the different curves. Okay, you can see when the point was on the circumference, there is a kink, but when the point is inside the circle, then we are getting this kind of a shape. When the point is outside the circle, then we are getting this kind of shape. Okay, and in the both of the curves we are not getting the kinks. So the another curve is the involute. The involute is a curve traced out by a end of a piece of a thread unwound from a circle or a polygon. So suppose there is a circle, or you can say you are having a ball, and around the ball or a circle there is a thread which is a thread that is wounded around the circle or a ball. So what we are doing, we are unbonding that thread. Okay, and the one end of the thread is fixed on that circle or a ball. So the curve traced out by that point that we are holding is called as a involute. So it may also be defined as a curve traced out by a point on a straight line. The straight line rolls without slipping along a circle or polygon. So on a circle, a straight line is rolling and without slipping. Okay, so then we are getting the involute. So involute of a circle is used as a teeth profile of a gear wheel. So involute is also very important in the mechanical engineering. So here you can see. This gear is holding a pencil, and the tip of the pencil is on the circumference of the circle. Okay, and this point is the end point of this line. So this tip of a pencil is fixed on this line, you can say that. So when this straight line is moving around this circle, the this line is rotating about around this circle, then the path traced out by then the path traced out for this point is called as a involute. So this is how your straight line is moving. You can see, and the path. Here is the another example how the straight line is moving around a circle without slipping. And this is the path of that point at the end of the straight line. So here is the another example of the involute. And so when we are unwinding the thread, which is which was wounded around the circle. Okay, so suppose your thread has a length of a 2 pi r, then one end of the circle should be fixed at this point, and the another end of the circle we are keeping it tight. Then we are getting the involute. So thank you very much for your kind attention. So in this video lecture, we have seen various type of curves and their basic, you can say, definitions. So in the next class, we are going to see how to draw them.